Okay guys, let's have a look at Pythagoras' theorem in 3 dimensions. It's even more exciting than Pythagoras' theorem in 2 dimensions, so let's go with this. Now, we know that many real-life situations involve 3-dimensional shapes. Shapes with length, width and height, of course they do. Some common 3D shapes which we could use would be boxes, which we're going to use, pyramids, which we're not going to use, so we'll leave you to practice on those, and right-angled wedges, which we will use. Okay, we're going to do 2 examples, one with a box and one with a right-angled wedge. Okay, there's some of the shapes. There's a box, there's a pyramid, and there's a right-angled wedge. Now, the important thing, this is the important thing with 3D shapes, is that in a diagram, a 3D diagram, well I mean a diagram representing a 3D object in a 2-dimensional plane like this screen is, the right angles may not look like right angles because we have to draw them with a kind of perspective to them, like a 3D perspective. So it is important, it is absolutely crucially important, I've found, to redraw sections of the diagram in 2 dimensions where the right angles are looking like right angles and can be seen accurately. I will show you as we go. Here's a first question. We've got a box here and we have to work out the length from a top diagonal corner right down to the opposite bottom diagonal corner G, which would represent the longest distance that you can travel throughout the inside of that box, I would think. Wouldn't you agree? I think so. Right, now, the first thing is to get a diagram, a 3-dimensional diagram, if you can, right? It is possible. These boxes aren't that hard to draw, so you can do that. And then you basically see what's going on. There's what we've got to work out, A to G, right? And what I'm going to do is I'm going to make up a triangle involving A to G, where A to G is the hypotenuse of that triangle. That's the base, right, from E to G, and there's the vertical height of it from A to E. And that little beastie there's a right angle, which doesn't look like one, but as you know it is, because that's like a wall, and that's like part of the floor, isn't it? Yeah, see, it's crazy, eh? So AG is the diagonal in 3 dimensions, yes it is. A right angle triangle, well I've just formed one, of which AG is the hypotenuse, can be formed as shown, alright? How are you going? Good? Great. Now if we know EG and AE, okay, then we can use dear old Pythagoras' theorem to find AG, because that's the hypotenuse, isn't it? You get it? Yes, now we do, this is very important, this bit, we do need to redraw all relevant diagrams in 2 dimensions so that they may be viewed front on, with line of sight at 90 degrees that is perpendicular to them, so that the right angles look like right angles, yes? Now, having said that, we know that we're trying to get these 2 sides here, right? So we can get this third one by Pythagoras' theorem. This vertical side here is 6 centimeters long because it's the same as BF, and this is a box, yes? So all the heights are the same. So that'll be 6. So that's going to be 6. Yes, it's going to be 6. Now we need EG. Now this is the problem because we haven't got EG. So we have to do some more work to get EG before we can actually engage with Pythagoras' theorem in this red right angle triangle. Okay, that's it. That is our mission now, to get EG. Once we've got him where we want him, we're laughing. Okay, now, all right, there's the floor. Now see, there's the floor. I'm looking at the floor from the sky so that all the right angles look like right angles, and I can sort of, you know, see what I'm doing without having to do my head in here. Now that's the diagonal. That's EG. That's what we're after in this calculation, right? And there are my distances that I know. That's that 10 centimeter, that's 10. This little beastie here is 5, which is the same as, that's that one, but it's the same as, is it? Yeah, same as this one, because it's a rectangular floor, because it's part of a rectangular box. Now we can get EG, can't we? We can see what we're doing, but that's a right angle, and it looks like a right angle, you see? Everything looks the way it should look, kind of, you know, to help clarify our thinking. Now, okay, so here let's go with Pythagoras' theorem. We got EG squared equals 10 squared plus 5 squared, which looks like 100 plus 25, which will get us 125. Therefore, EG would be the square root of 125. Okay, now we've got him. Now we're going to go back to the right angle triangle now, that red right angle triangle here, but we're going to draw it in 2 dimensions so we can see what we're doing, guys. There it is. There it is. Look, that's that triangle there. See that triangle there, drawn so that this right angle looks like a right angle here. That's 6, that's the height, and we've just found out EG, which is this beastie here, right? That's root 125. So now we're going to do Pythagoras' theorem on this triangle to get AG, and AG is what we're after ultimately for this question. Are you good? Great, let's go. Pythagoras' theorem, AG squared equals AE squared plus EG squared. Yes, we know that. And put the numbers in. That'll be 6 squared, or 36, plus root 125 squared, which is just 125, because you know that, don't you? The square of the square root of something is just a something. Yep, you got it? Good. So that'll get us, what's that come to? 161. Therefore, AG will be the square root of 161. Now, did they want it in any particular... No, they didn't say anything about decimals, so we'll just work it out as decimals anyway, just to cover our bases. It's 12.69 centimetres, that's to 2 decimal places, but root 161 would have been perfectly correct. Actually, when you get into year 12, they actually say they want an exact answer unless they ask for decimals, so that would be the answer, 161, root 161. Alright, how'd you go? You get it? Terrific. So let's go over the screen and see what else we've got. Now this is our wedge. This is our wedge question. So what we've got here is a piece of cheese in the shape of a right angle wedge. It's sitting on a table and it has a rectangular base. We definitely need a picture, guys. 14 by 8, and it's 4 centimetres high at its thickest point. Yes, I sort of get it. And an ant crawls diagonally across the sloping face. Goodness, we need a diagram. Let's draw a diagram. Well, there it goes, and look, someone drew it for us, so that's very convenient, isn't it? There's the base, 14 centimetres by 8 centimetres. Good. Now, what have we got to say here? It's 4 centimetres thick at its thickest point, so that looks pretty good, doesn't it? Yes, and it's a right angle wedge, so that little beastie in there is a right angle. And this ant, goodness, that's not very good for the cheese, is it? This ant crawled across the cheese from B to D across that face. So we've got to get BD in centimetres. And this is a worded question with no diagram, so we have to express our answer in words at the end, remember? Yes, that's the convention that we're using. So how are we going to do this, guys? Well, I'll tell you what. You have a little think and come back, and then I'll show you what I would do. Okay, goodbye. You back? Hello. Now, this is what I did. I said the ant's path is BD, and I need a two-dimensional diagram. So the face along which the ant moves, looked at front on with a perpendicular line of sight, looking at that face directly, that face there would be looking like this. Now that's a lot better. The right angles look like right angles again. This is 14. This is, oh, I don't know what that is, do I? Oh no, I don't. CD, they didn't tell us CD. Tricky. Well, I think we need to find CD. Once we find CD, we can use Pythagoras' theorem with CD, which is the same as this one, BA, and this 14 to get the ant's journey. But we don't know that, so that's what our mission is. Should we choose to accept it? And of course we do. So what are we going to do to get CD? I think we need another diagram, don't you? Yes, if we knew CD, as I was saying over there, we could use Pythagoras' theorem to get BD in that rectangular diagram, yes? So let's see about CD. To find CD, we need another two-dimensional diagram. Now, can you pick it? Can you see where it is? I think you can. There it is. It's this bit here, looked at front on, right? So the right angle looks like a right angle. And CD is this beastie, right? The same as this beastie here, right? So we've got 8 centimetres there, 4 centimetres there. It's easy peasy to work out CD. So by Pythagoras' theorem again, guys, we can say that CD squared is equal to DF squared, which is 8 squared, plus FC squared, which is 4 squared, which gets us 8 squared plus 4 squared. What's that? 64 plus 16. What's that come to? 80, I think. Yes. So therefore CD is root 80. Good show. Now we can go back to here and use it in here to get this length, right? The diagonal or the hypotenuse, right, of this triangle over here, BAD, if you like, because CD will be the same as BA. That's how it works. Alright, so now, in the rectangular diagram on the left, let's go for it, guys. This is our moment of triumph here. By Pythagoras' theorem, we can say that BD squared will be CD squared plus AD. Did I get all that right? Yes, I did. Yes, it all works. So therefore, that's root 80 all squared, which is what CD was, root 80, all squared plus 14 squared. That's this one here, right? Now, I happen to know that 14 squared is 196, and root 80 squared is just 80. So what does that come to? 276, I think. Yes. So therefore, BD will be the square root of 276. Good gracious me, is that what we have to find out? Yes! But you always must read the question before you leave it, because it might be asking for something which we've forgotten about. Now, what did it say? Yes, how far to the nearest millimetre? Oh my goodness, we've got centimetres here, so I think we better do that on the calculator. Do that on the calculator, work out what it is in decimals, but that's in centimetres, isn't it? Yes, 16.61 centimetres. Now, we've got to get that into millimetres. If we're going to quote this to millimetres, we have to convert that into millimetres now. See, if we hadn't read the question before we left it, we would have got this wrong. How far to the nearest millimetre does the ant walk? Okay, now to get from centimetres to millimetres, you've got to multiply this little beastie by 10, of course, because there's 10. Yes, that's what we're doing, guys, to the nearest millimetre. Over the screen we go. Now, if the ant travels 16.61 centimetres, that would be multiplied by 10. What do you get, guys? Yes, 166.1 millimetres, but we're asked for it to the nearest millimetre, so we have to round off the nearest whole millimetre. Yep, so it's going to be 166, and I think that's our answer to the nearest millimetre, and I've put it in words, haven't I? Which is what we have to do, put a box around it, and everything's good. That, guys and gals, is our answer. Yes? And we wish the ant wasn't there in the first place, but he did travel 166 millimetres across our cheese. Here's the remember. In Pythagoras' theorem, we can use this in three-dimensional situations, which we've just been doing. Some 3D shapes include boxes, which we did use, pyramids, which we didn't use today, and right-angle wedges, which we did use. And to solve, this is the crucial bit here, to solve problems in 3 dimensions, it's very helpful to draw sections of the original shape in 2 dimensions to untangle our thinking and clarify what we need to do. Okay? Yes, that's it. That's the secret, that number 3. And you're a star, and huzzah! So please go far and practice. Lots of practice for you, okay? Get good at 3D, and please learn how to draw a box and 3-dimensional shapes in basic form, okay? Because it's a really useful skill. I'll see you next time. Thanks for coming, and see you later.